University of Texas.
Sorry, I just remembered.
University of Texas Groups and Dynamics seminar. So this is an honor, especially that I know very little about dynamics and I know less about groups. But nevertheless, I very much hope that today I will be able to tell you something that will be interesting from your perspective. So this is what I would like to talk about, is this recent result that random interlacement is a factor of i.i.d. So I will spend some time carefully defining random interlacement, and I guess I don't have to introduce factor of i.i.d. That is the part that you're more familiar with, but the interlacement part is also fun too. So my name is Balazs Rath. I am from Budapest, from University of Technology and Rényi Institute, and this is joint work with two young researchers. One is called Sándor Rokob. He's a PhD student at University of Technology, and Márton Borbényi, who was actually a master's student when this finished. So I think he started the PhD one day after we submitted the paper. But I'm not the advisor of either of these young gentlemen. All right, so let's begin with the definition of random interlacements. And I think the most natural starting point is to first define it on the d-dimensional lattice. And there's a typo there because the d should be greater than or equal to 3. So now let's assume that the dimension of this lattice is at least 3. So that's, yep. But then I will go to more general settings. But chronologically and pedagogically, this is the point to start. So let's consider a random walk on the d-dimensional torus, integer torus with side length n. And I'm going to denote this random walk by xn. So the location of the walker at time n is xn. And let's start this random walk from a uniformly chosen starting point on the torus. And I'm also going to fix a positive parameter u, and I'm going to denote a general vertex of the torus by x. So here's a quick remark. So if you run this random walk for u times n to the d steps, then it's going to visit a positive fraction of the vertices of the torus. This is because the dimension is greater than or equal to 3. So therefore, the random walk is locally transient. This means that indeed, the number of vertices visited by this random walk is going to be proportional to a positive fraction of the volume of the torus, which is n to the d, of course. And since I started from a uniformly chosen point, the expected number of visits to one particular point is going to be comparable to this parameter u. Oh, by the way, if you have questions, don't hesitate to stop me. Let me denote by the trace, let me denote by I superscript un, the trace of the random walk if you run the random walk up to u times n to the d steps. So this is this I superscript un, this is a random subset of the torus. It's the law of this random subset is invariant under translations of the torus. And somehow we want to keep u fixed, but let n go to infinity and see how this random subset that consists of the sites visited by the random walk, how is it going to look locally? And here's a theorem about this. So if I pick a a finite subset of ZD. So here is how, by the way, can you see the cursor as I'm pointing at things?
Yeah, looks
Okay.
good.
So, so if I choose a finite subset of ZD and I fix this parameter U, then of course, if the torus is big enough, then you can imagine that this finite subset of ZD is also a finite subset of the torus. Then I claim that the probability that this random subset that I defined above avoids my set K, so this probability, this will converge as n goes to infinity. And what it will converge to is e to the minus u times the capacity of K, where I will define the capacity of K in a second. But before I go into the details, let's just say that the capacity of this set is just a way to measure the size of the set. It's something like volume, but it behaves a little bit differently. Nevertheless, the bigger the set, the bigger the capacity of the set, and hence by this formula, the smaller.
So excuse me.
Yeah.
So do you start at a random point, or in
I
this?
start at a uniformly chosen starting point.
Okay.
So I choose. So I made that's a way to make this random set homogeneous. So this, of course, the bigger the capacity, the smaller this probability. And of course, if you look at this parameter u, of course, if you make the parameter u bigger, that means you run the random walk a bit longer. That also decreases the probability that this random subset avoids the set K. But I did not yet define the capacity of the set K. So I will spell out these formulas, but the capacity is the sum of the escape probabilities. If you sum over the vertices of the vertices in K. So this capacity of K is sum over all x in K, the probability that if you start a simple random walk, but now on ZD. So now imagine that this K is a subset of ZD, and you start a simple random walk on ZD. What is the probability that this hitting time of K is plus infinite, or actually it's not hitting, sorry, it's called hitting time. So hitting time is just the first step, not counting step 0, when this random walk that I denote by yn returns to set K. But of course, if this hitting time is infinite, that means that the random walk escapes. And if you sum these escape probabilities, then you get this so-called capacity. And of course, this is where I use that the dimension is greater than equal to 3, because if you consider random walk in 2 dimensions, then of course this escape probability is 0, because the random walk is recurrent, as opposed to dimension greater than equal to 3 when the random walk is transient. So this is a funny notion, this capacity. For example, from this definition, it's absolutely not obvious to see that capacity is monotone. Namely, if one set contains the other, then the bigger set has a bigger capacity. So you cannot see that from this definition, but capacity has many different definitions, and this fact follows from other definitions. So this is a theorem by David Windich, who was the PhD student of Alan Sznitman, who came up with this notion of interlacements. Nevertheless, so there was this random subset of torus that I denoted by IUN, and this fact, this theorem of David Windich, already implies that this random subset converges locally in distribution to some random subset of ZD as n goes to infinity, meaning that if you make this torus bigger and bigger, then the probability of cylinder events is going to converge. And namely, this theorem alone shows that there is a random subset of ZD which has the probability, which has the property that the probability that this set the void set K is e to the minus u times capacity of K. And by the way, this formula already uniquely determines the law of this random subset by simply the inclusion-exclusion formula. So there is a subset with this property, and there is a unique random subset with this property. And this random subset is called the random interlacement at level U, as defined by Balazs Sznitman 12 years ago, or actually a bit earlier, but it took a couple of years to finally the paper to appear. So, and by the way, it's again a non-trivial fact that, so instead of capacity, I could imagine other monotone functions or a monotone set function, and it's not guaranteed that a random subset satisfying this property would exist. But this formula indeed defines a random subset, and it's called random interlacements. So, and of course, one property that comes out from the theorem of David Windich, or even from this formula, is that the law of the interlacement is invariant under the isometries of ZD. So if you shift random interlacement, or if you reflect it, then it's going to be random interlacement. It has the same law. Nevertheless, this definition with this formula is a bit implicit. So let me give a more explicit construction of this random subset of ZD. And what I will do is I will construct it as the set of sites visited by a cloud of doubly infinite trajectories. So let's go into the details. So we need one slide of definitions for this. So let me denote by W the space of doubly infinite transient nearest neighbor trajectories on ZD. By transient, I mean doubly infinite trajectories that go to infinity in both directions. And I will denote one such doubly infinite trajectory as Wn, where n is any integer number. And curiously enough, I will define time shift equivalence on this space of doubly infinite trajectories. So I will see, I say that two trajectories, W and W prime, are time shift equivalent if there exists a K, such that one trajectory is the time shift of the other by K. Somehow this is going to be a very convenient notation to if one wants to define interlacement. And I'm going to define W star, the space of doubly infinite trajectories modulo time shift. So this W star is the set of equivalence classes under this equivalence relation. And I will also need to define the projection map pi star, which maps to each trajectory of ZD its equivalence class modulo time shift. I will also define, so if there is a K, this K, in this talk, K will denote a finite subset of ZD. So WK is just the set of doubly infinite trajectories that ever visit this set K. And WK star is just the same, but with trajectories modulo time shift. And if I have a trajectory, then I denote the trace of this trajectory, the set of sites visited by this trajectory. And if I have a trajectory modulo time shift, then again, I define the trace of this doubly infinite trajectory modulo time shift to be the set of sites visited by this element of V star. By the way, if this bottom line, is it still visible? Okay.
Yeah, it is.
Yeah.
Okay. So, So this the important space that we will work on is this W star. Again, the space of doubly infinite trajectories modulo time shift. So here's the theorem. There exists a measure, and it's a sigma finite measure. A sigma finite measure on the space of doubly infinite trajectories modulo time shift, such that if you consider a Poisson point process on this set. So if I denote by x superscript script u to be a Poisson point process on this space, where the intensity measure of this Poisson point process is this parameter u times this measure nu, then first of all, this cloud of trajectories, this Poisson point process of trajectories, the law of it is going to be invariant under the isometries of ZD. And if you look at this cloud of trajectories, then the interlacement at level U is going to be the set of sites visited by this cloud of trajectories. So this is the constructive definition. It might be a bit scary for those of you who are not that familiar with Poisson point processes. So the notation here is that this x superscript u, it's a point measure. So there's a countable collection of doubly infinite trajectories. And actually the good notation is that this is a point measure. So this delta is just Cronach, it's Dirac delta, a Dirac measure concentrated at a trajectory. So Wi is trajectory I, where I ranges over an abstract index set. And it's, yeah. So this is a Poisson point process is a point measure on the space of doubly infinite trajectories. But if that's too hard to imagine, just imagine an accountably infinite collection of doubly infinite trajectories. But somehow this whole picture is invariant in translation under translations, in the sense that if you shift this cloud of trajectories, then you get a cloud of trajectories with exactly the same distribution. Yeah. So this is the constructive definition, but again, it's a bit abstract. So let me give one more try at making it more user-friendly. So how does this Poisson point process of doubly infinite trajectories look like? Well, if I have a finite subset of ZD, how does the restriction of this point measure to the set of trajectories that hit the set K? So I have this cloud, but let us focus on those trajectories of the cloud that visit a set K. And now this has a rather simple definition. So this smaller cloud, the cloud that hits set K, can be generated in the following way. For each vertex of K, consider Poisson U number, so a random number of doubly independent doubly infinite trajectories, each of them starting at K. So for each vertex of the set, you put down Poisson U number of doubly infinite random walk trajectories. A doubly infinite random walk is like you run random walk in the forward direction, but also you run a random walk in the backward direction. So you get a doubly infinite random walk, which is at x at time 0. So you do this for all vertices x, but then you do a little bit of censorship. You throw away a couple of trajectories. Namely, you throw away those trajectories whose backward part ever returns to K. So if it's a doubly infinite trajectory, but if there's ever a strictly negative index that visits K, then you throw this trajectory and you don't consider it. So you keep only those trajectories whose hitting time is at time 0 at this set. All right, so you throw away a couple of trajectories. Then what you do is you take the time shift equivalence class of the remaining trajectories, and voila, what you obtained is the restriction of random interlacement to those set of trajectories that hit K. So this is maybe the user-friendly definition. And the theorem behind this is that if you look at a bigger set, look at the trajectories that hit that set, and then you restrict, and then you take a smaller set, and further you throw away those trajectories that that do not hit this smaller set, then you get a consistent rule. It's the same thing. So this definition is self-consistent. So indeed, there is a point measure defined as I claimed, and that's random interlacement. Sorry for the awkward phrasing. So this is a strange subset of ZD, and this is a strange Poisson point process on the space of trajectories. But there is good reason to make it a tiny bit more complicated. So let's make it even a bit more complicated. So let's define the interlacement point process. Namely, the full definition is you take a Poisson point process on the set of labeled trajectories. So each trajectory now has a label, and the label is just a positive real number. So this is going to be a Poisson point process on the space of doubly infinite trajectories times the set of labels. And the intensity measure of this Poisson point process is this measure nu from the previous theorem, and product measure of that with Lebesgue measure on the set of labels. So now this is a big cloud of trajectories because, for example, in the previous definition, when you only considered this, then every site was only visited by a Poisson number of, every site was visited only by a Poisson number of trajectories, while here, every vertex is visited by infinitely many trajectories. Nevertheless, if you consider only those trajectories that have label less than u, then you get back the previous definition. You get back this Poisson point process at level u. So in some sense, this interlacement point process, this labeled process, is the mother of all of those processes that we have. You can obtain each and every of those guys if you just if you restrict the set of labels. And this X, this Poisson point process on the set of labeled doubly infinite trajectories modulo time shift, well, this is what we call the interlacement point process. All right. So if this wasn't complicated enough, here's another jump in abstraction, because whatever I said previously that worked on the d-dimensional space, the same construction works on any locally finite connected transitive transient infinite graph. So the important part is the transient. So a graph is transient if random walk on it is transient. And this is the thing that you need. So if you want to define interlacement, you need your random walk to be transient. And this is, so this more general construction on of random interlacement and the random interlacement point process on any general graph, this was done by a PhD student of Sznitman called Teixeira. I mean, a former PhD student. So, and from now on, we will consider random interlacement on such a graph, transient transitive graph. As a matter of fact, Teixeira's definition works in even a more general class, namely any weighted graph, and you don't even need transitive, you only need transient. But for this talk, graph is any transitive transient graph, locally finite connected. And nevertheless, if you consider simple random walk on this graph and you define interlacement using this random walk, then the law of this Poisson point process is still going to be invariant under the automorphism group of G, and I'm going to denote automorphism by phi. So this is great. Why is this interesting? So this is a little motivational slide for those of you who are not that familiar with random interlacements. So, well, for example, the seminal paper of Sznitman has 233 citations. So there is a couple of us working on this field. We call ourselves the interlacement community that I'm a proud member of. And for example, here's maybe a result that might get you excited. So here's a result by Teixeira and Johan Tukesson from 2013. So this is going to be a characterization of amenability using random interlacements. So this graph, this transitive transient graph, is going to be amenable if and only if the interlacement set is going to be connected in the ZD nearest neighbor sense for arbitrarily small values of the intensity. So, you know, smaller the intensity, so this U is called the intensity parameter. The smaller the intensity, the smaller the set. Nevertheless, if your graph is amenable, then this random subset, this that consists of these walks or the trace of them, is going to be connected for arbitrarily small densities, if and only if G is amenable. So that's already a fun fact. Most of the literature on random interlacements is concerned with the percolation of the vacant set of the interlacement. So I myself wrote a couple of papers on this, and I will not say more about this. Nevertheless, if you like Gaussian free field, that's also a nice random spatial process defined on the set of vertices of a graph. So if you're into GFF, if you're into Gaussian free field, then actually good news is there are so-called isomorphism theorems that connect random interlacement, or rather the local time of random interlacement, to GFF. So this is very nice theory. Again, I'm not going to talk more about it. But here is one more thing. So this is a paper by Tom Hutchcroft from 2018. Actually, if you have this random interlacement point process X, then you can construct a wired uniform spanning forest on the graph G. So the wired uniform spanning forest is a spanning forest of this graph G. And if you remember this X, what was it? It was a countable cloud, or a countable collection of doubly infinite trajectories, modulo time shift, which also had labels. And here is, you can define the wired uniform spanning forest from an interlacement in one line, using what Tom Hutchcroft calls the interlacement Aldous-Broder algorithm. So that's it. So just collect the smallest label first entry edges of this cloud, meaning for every vertex of the graph, look at the trajectory, look at the interlacement trajectory with the smallest label that goes through this vertex. Now pick the trajectory with the smallest label and look at the first time when it enters this vertex, and add to your graph the edge where the random walk, the trajectory, entered your vertex. So you can check that what you created is a spanning forest of the graph, and as a matter of fact, it's the so-called wired uniform spanning forest. And now that I'm talking about it, I think Tom Hutchcroft was there in 2016. So when I was there in at College Station at that conference in Texas, organized by Eviatar Procaccia, who's also a member of Interlacement community. I think Tom was there, and he already mentioned this theorem that he had. And it's a very nice way of constructing wired uniform spanning forest from the interlacement. Now, having said this, shown you this motivational slide, now let me get to our result. So here is our main result. It is, as the title of the talk says, random interlacement is a factor of i.i.d. So let's discuss that. So again, let me remind you, my graph G is a locally finite, connected, transitive, transient, infinite graph. And one more notation. So this interlacement point process, this is a point in a space, namely it's a random, this X, this interlacement point process, it's an element of this space, the space of point measures on the set of W star cross R. So the set of labeled doubly infinite trajectories modulo time shifts. So here is our theorem. Well, it just says that it's a factor of i.i.d. So there exists a probability space omega A nu and the measurable map E, which maps. So on each vertex, so there is a map that if you have an element of omega for each vertex of V, then it can construct an element. So this T, given some input on the set of vertices, it constructs an output, and this output is a doubly infinite, it's a cloud of doubly infinite trajectories with labels. And then there are two things, namely, if you plug in as an input, if you plug in i.i.d. input, these etas, and so there's i.i.d. input on all vertices of V, and I put together from it this collection eta, and these are i.i.d. with distribution nu, then what my algorithm or what my T spits out is a point process. It's an interlacement point process. So it's a Poisson point process on the space of doubly infinite trajectories with the required intensity measure. So it's an interlacement point process. Moreover, for any automorphism of G, my map intertwines with that automorphism. So if I push my input with the automorphism and apply my map, that's the same thing as applying my map and then pushing the output with the automorphism. And here, if I have a collection of labeled trajectories and an automorphism phi, then of course the image of the point process or the image of this collection of trajectories under this automorphism is just you apply the automorphism to the trajectories pointwise. So you push the trajectory with the automorphism, but you leave the labels alone. And of course, you push the input, these i.i.d. input with phi in the usual way. So that's factor of i.i.d. So this is our result. And well, why is this interesting? So I will try to make this, so I'm not done yet. I will do more convincing why this is an interesting result and why it is a non-trivial result. Nevertheless, mention that a fun corollary. So it follows from our theorem that wired uniform spanning forest is a factor of i.i.d. because we constructed the interlacement as a factor of i.i.d. and this interlacement Aldous broader algorithm of Tom Hutchcroft constructs the wired uniform spanning forest as a factor of the interlacement. By the way, this was known. So this was already this result was already stated in various papers of Russ Lyons, including this famous one, and a full proof is spelled out by Omer Angel, Gurabrey, and I'm not sure how to spell the Spinka in a recent paper. So this is one corollary, but let me try to also convince you that our result is not entirely trivial. And also this might highlight the fact why we need the space. So this, it might seem strange that we needed this space W star. So why can't we work with W? Why can't we work with the space of doubly infinite trajectories? Why do we need this modulo time shift equivalence? So here's another result. Well, let me begin with a rather simple claim. The claim is that if there exists a Poisson point process, let's denote it on Z, which is like the interlacement, but it lives on the space of doubly infinite trajectories without time shift. So W plus R, not modulo. So if there is a point process on the space of doubly infinite trajectories, labeled doubly infinite trajectories, such that the law of this point process is automorphism invariant, or equivalently, its intensity measure is invariant under automorphisms. Moreover, if you take the modulo time shift of this, you get the interlacement point process. So if there exists a point process on labeled doubly infinite trajectories, which is invariant under all automorphisms, and it maps under the natural projection to an interlacement. So if this happens, then this process Z is going to be a factor of i.i.d, and therefore the interlacement itself is a factor of i.i.d. So what I'm saying is that this is the first idea to make the conclusion that our point process, the interlacement point process, is a factor of i.i.d. So if this condition number one holds, then Z is a factor of i.i.d. And if it additionally maps to interlacement, then this mapping is a factor map. Therefore, interlacement is a factor of i.i.d. So let me stress that this claim is not complicated. So this is a cheap fact. Why? Because if you have a Poisson point process on the space of doubly infinite trajectories, then you can very easily decompose it into essentially i.i.d pieces, namely decompose this point process according to, just look at the location of each of these trajectories at time 0, and that has to be a vertex, and these, so you decompose this point process into essentially i.i.d packages. One package consists of those trajectories that hit a particular vertex at time 0. And these are disjoint packages, and they are i.i.d, and this is our proof. So essentially, this is a rather easy claim. And here's the fun fact. So this would be the cheap construction. This would be the cheap construction of the interlacement, but we have a theorem saying that this cheap construction only works for very weird graphs. Namely, the cheap construction, so there exists a point process Z that would give a cheap construction of the interlacement point process. So this exists only if and only if my graph is non-unimodular. And for me, those graphs are weird. Well, okay, I guess you're familiar. The most easy example is the so-called grandfather graph of Trofimov. As a matter of fact, that was the first case when we realized that there is a cheap construction, but then we realized that, well, okay, so more importantly, if your graph is unimodular, like ZD or D regular tree, then there is no cheap construction like this. Then you have to prove that it's a factor of i.i.d using different methods. And by the way, this whole thing, why you have to take the space of trajectories modulo time shift. So this whole idea already appeared in the seminal paper of Sznitman, but of course he only discussed it in the case of ZD. But nevertheless, this is already a nice characterization theorem, because if you remember, there was an earlier characterization theorem which characterized amenable graphs using interlacement, and now we have a characterization of unimodular graphs using interlacement. Okay, how much time do I have left?
Well, we usually go to around 2:55 or 2:50, depending on how much time you want to leave for. Yeah, so like you have like 10 minutes.
Okay, sounds great. Sounds great. Yeah, so this is, I'm going to disappoint Luis a little bit because probably he wanted much more technical details.
Yes.
Okay, so here's a few words about the proof. So I'm not really going to discuss this non-unimodular part. That's very fun as well, very much fun. But let me focus on the proof of our main result. And the last, so these are ideas. So just relax, not many formulas. So this is just going to be like a fairy tale. And sorry, if you want, the paper is on archive and it's rigorous. But now let me just tell a nice fairy tale about the ideas of the proof. So, and even to make things simple, let's forget about the labels. So let's just construct this point process that I called X superscript U, which is just a collection of doubly infinite trajectories modulo time shift. So this is interlacement point process at level U, no labels. Let's focus on the proof, how to show that this is a factor of i.i.d. So the idea that comes from Lewis, the first printed account of this idea, is that we can approximate the interlacement point process with something called finitary random interlacement. So let me define that. So let me define an auxiliary point process, but this is going to be a Poisson point process on the space of trajectories that have length t. So space of nearest neighbor trajectories that have length exactly t. I know that Luis did not define it like this. For him, these trajectories had random length, it had geometric length, and that has advantages. For our case, it's more beneficial to consider these trajectories of fixed length. By the way, we like to call them worms. Okay, so let's worms of length t. So this X superscript ut is going to be a Poisson point process on the space of worms. Namely, the definition is super simple. Start Poisson number of random walks of length t from each vertex of V. That's it. For each vertex, you pick a random number that's going to be the number of worms emanating from that vertex, and each of the worms are independent random walk of length t. And the number, so note that this is a Poisson variable with parameter u divided by t. So the longer, so you have this parameter in your mind, u, but the longer the trajectories, the fewer walkers you start, because the fewer of them you need. So longer trajectories means less trajectories starting from a point. And then here's a rather simple fact. This point process, so this collection of worms, is a factor of i.i.d. pretty much the way I define them. So there's like independent package for each vertex. So this is a factor of i.i.d. And here's another fact, which one version of this fact was proved in the paper of Lewis. Namely, if you let t go to infinity, so you make these guys longer and longer, but you start fewer and fewer of them, then the limit in distribution, so these guys, as t goes to infinity, converge locally in some sense to the desired random interlacement point process. So somehow as they get longer locally, they start to look like doubly infinite trajectories because you see them come and go, but you don't really see where they come from. And the reason why you only consider them modulo time shift because you can't even really tell when they started. So that's why you have to consider them modulo time shift. So there's this fact that for each finite value of t, finitary interlacement is a factor of i.i.d. And here's this other fact that this converges locally as t goes to infinity. Let me stress, if you put together these two facts, you still cannot conclude that the limit object is a factor of i.i.d. So there are counterexamples that weak convergence does not preserve the factor of i.i.d. property, does not necessarily preserve. So how do we boost this construction? What we do is we actually provide the so-called coupling of this sequence of interlacements where the length is 2 to the n, so that not only do they converge in distribution, but actually they converge almost surely. So on a joint probability space, we can make a realization of finitary interlacements with increasing length such that they almost surely converge to something locally. Moreover, our whole joint construction is a factor of i.i.d. And if these two things hold, then the limit that they converge to has to be factor of i.i.d. too. So that's the idea that we boost convergence in distribution to almost sure convergence. So I still have 3 minutes to talk about how we do that. And that's fun. So stick around, 3 more minutes to go. Okay, so we can conclude that this is a factor of i.i.d. So how do we do this? The reason why the length, so we are doubling the length. What we are doing is we are doubling the length of worms. So we want to couple point process with length t. So this worm point process of length t with worm point process of length 2t, we somehow want a joint construction of these two guys so that locally they look similar. So if they are very long, then locally you cannot really tell which point process it was. So how do we do that? Okay, so some more details. So more specifically, we will provide a construction which starts with point process of worms of length t and some extra i.i.d. randomness. Then we do some magic, and then what we spit out is a point process of length of worms with twice as big of length. So now the worms became twice as long. And so what happens is that the length of these trajectories somehow magically doubles, but the intensity of the starting points is half as big. So you get twice as long trajectories, but in some sense, half as many of them. And of course, what has to happen is that we somehow start with our input, we split it into 2 parts with coin flips. So for each worm, we flip a coin, and if it's head, then we put it in this first point process. And if it's tails, then we put it in this second point process. Still, both of those guys have length t. But of course, the intensity is only half as big because half of the trajectories went to the first collection and for the first cloud and the second cloud. And then what we have to do is we somehow have to concatenate these worms. So somehow we have to find a pair to most of these worms. We want to concatenate and make a worm which is twice as long. So this is a very naive picture, but it would make sense. So if we could find a pair to, well, not all of them, but to most of them, and somehow stick them together and make a worm which is twice as long, then we are done. So that's how we form, and then try to find a pair to many worms and create worms of length 2t. So that's the plan. And how do we perform this mating of worms? So we divided them into 2 groups, and now we want them to mate. The big idea here is that we do not force one guy to end at the point where the other guy starts. That would be too restrictive. So we don't want them to exactly match, but we want to connect them with some sort of rubber band, an elastic band. And that elastic band is going to be a random walk of length L. So somehow we want to collect the endpoint of worms from group 1 to the starting points of worms from group 2. We want to connect them with a simple random walk of length L, where this L is long, but certainly much shorter than the length T. Okay, I'll finish in 2 seconds. And this magic, this surgery or this mating, this is done by a very nice technique from the theory of random interlacements called the soft local time method. And it breaks my heart, but I don't have time to discuss this. But this is the magic part. So this can be carried out rigorously and effectively. Nevertheless, since I introduced an intermediate elastic band of length L, now I did not obtain what I was shooting for, because now my worms have length 2t plus L, because there is an intermediate random walk. So we have to trim off, we have to cut off a portion of length L from the end. So somehow this is the surgery part, but somehow, even intuitively, somehow there is a trade-off. If one has to choose this L optimally, because if you make this elastic band bigger, so if make you L bigger, that makes the matching easier, because you can find pair from farther points. So matching is more successful is L is bigger. Nevertheless, because of this surgery that you inserted a part in the middle, but you cut off something at the end, the local picture is going to be less similar. But I mean, the local picture. So if you remember, you started from these guys of length T, and then you ended up with these guys of length 2T, and you want them to look locally similar. And if L is big, then the local picture is going to, because of these surgeries, it's not going to be that similar. So one has to find the optimal value of L, and this is just a fun fact. So this is how you have to choose. In our paper, this is how we choose L as a function of T. So you don't have to see this. What the point is that this is a power of L, and the reason why these powers do appear is that there is another power here. Namely, there is a very strong heat kernel bound. I will finish in a second. So there is a heat kernel bound for simple random walks on a transitive graph. So if you have a transitive transient graph, then the probability that if you start a random walk of length L from X, the probability that at time L it is at Y is bounded by this universal constant. And this constant tells you that in some sense, this heat kernel is the probability of, let's say, returning to the origin decays like this. And the message is that the worst case scenario, the worst graph from our point of view is the 3-dimensional lattice. So the heat kernel of any other transitive transient graph decays faster than that of the 3-dimensional lattice. And by the way, this is something that we had to put together from deep results. So I just mentioned these names to make you happy because you wanted groups. So this is a group theory seminar. So there are very deep theorems from group theory by Gromov, Trofinov, Salovkost, and Coulon, and then some probabilistic ideas from Morris and Perez, which together imply this. But by the way, is this a known fact? Because we had the sense that this is a folklore fact, but we never found the proof. So like general heat kernel estimates, if you're aware of a proof of this, then we can drop the appendix of our paper, because this is like we have a, I don't know, 5-page or 8-page appendix to our paper where this result is proved, but that's not our result. This is folklore, as Gabor Pete told us. but we never found it. So if you can help us with that, then we would be helpful. And sorry for running out of time, and thank you for your attention.
Okay, let's thank Bella. Thanks, very nice talk.